Unit 2 of Chemistry, Electrochemistry. The objectives of this chapter being describe an electrochemical cell and differentiate between galvanic and electrolytic cells, apply Nernst equation for calculating the EMF of galvanic cell and define standard potential of the cell, derive relation between standard potential of the cell, Gibbs energy of cell reaction and its equilibrium constant, define resistivity, rho, conductivity and molar conductivity of ionic solutions, differentiate between ionic, electrolytic and electronic solutions, electronic conductivity, describe the method for measurement of conductivity of electrolytic solutions and calculation of their molar conductivity, justify the variation of conductivity and molar conductivity of solutions with change in their concentration, and define molar conductivity at zero concentration or infinite dilution, enunciate Coriolis law and differentiate its applications, understand quantitative aspects of electrolysis, describe the construction of some primary and secondary batteries and fuel cells, explain corrosion as an electrochemical process. These are all the objectives of this lesson and what you will be learning in this lesson. So let's start. Chemical reaction. The primary definition: chemical reactions can be used to produce electrical energy. Conversely, electrical energy can be used to carry out reactions that do not proceed spontaneously. This is the main definition of the chapter Electrochemistry. Chemical reactions, normally we can make chemical reactions produce electricity or generate electricity, or in other way we can use electricity to do non-spontaneous chemical reactions. They are again giving the definition: electrochemistry is the study of production of electricity, generation of electricity from released during spontaneous chemical reactions, and the use of electrical energy to bring about non-spontaneous chemical transformation. Electrochemistry is the study of production of electricity from chemical reactions or spontaneous chemical reaction. Or another way of electrochemistry is using electricity to conduct non-spontaneous chemical reactions. The subject is of importance for both practical and theoretical considerations. A large number of metals, sodium hydroxide, chlorine, fluorine and many other chemicals, a large number of metals, sodium hydroxide, chlorine, fluorine and many other chemicals are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on large scale in various instruments and devices. In any device you see, it needs a battery or depends on electricity. And many of the metals, sodium hydroxide, chlorine, fluorine and many other chemicals are produced via electrochemical methods. The electrochemical methods are of using electrical energy to bring about non-spontaneous chemical reactions, or the generation of electricity from spontaneous chemical reactions. The reactions carried out electrochemically can be energy efficient and less polluting. The reactions carried out electrochemically can be energy efficient and as well as less polluting. Therefore, the study of electrochemistry is important for creating new technologies that are eco-friendly. The transmission of sensory signals through cells to brain and vice versa, and communication between the cells to the cells are known to have electrochemical origin. From brain, the impulse is taken from the sensory organs, the impulse is taken to the spinal cord, then the brain, then the reaction is taken again to the muscle effector. All these transfers or signal, it is via electricity. They are found to have electrochemical origin. Electrochemical transmission of signals or nerve impulse. So therefore electrochemistry is therefore a vast interdisciplinary subject. In this unit we will cover only some of its important elementary aspects. This is the Daniell cell, which comes under the galvanic cells. The electrochemical cells are of the two types. One is galvanic cells, and two electrolytic cells. Electrolytic cells. The galvanic cells, which we produce electricity from chemical reactions, is what we call galvanic cell. Here electricity is produced. In the electrolytic cell, electricity is used to conduct non-spontaneous chemical reactions. Under the galvanic cell, we study our Daniell cell, which is this one, a solution, two anode and cathode, which are the two electrodes in two solution, with zinc being the anode and in the zinc sulfate solution, and copper being the cathode in the copper sulfate solution. In this solution, how this works is, in this solution the zinc are found to be in the state of Zn2+. The zinc here will continue, the zinc deposited on this electrode will give off electrons and go into form zinc 2+. The electrons will remain here and go to the second electrode made of copper. Here the zinc atoms on the anode or the electrode will dissolve into the solution to give electrons, which will be transferred here. See the electron flow, it will be transferred here. In here, the Cu2+ in the solution of the copper sulfate solution will take these electrons, which will flow here and deposit on the electrode. The zinc on the electrode will dissolve into the solution, forming zinc 2+, giving the electrons to the electrode, causing electron flow, The current direction is opposite to the direction of the electron flow. And the copper ions in the solution will take up the electrons coming from the zinc and will be deposited on the copper electrode. This is the flow of charges which will lead to the flow of current. Salt bridge is used to maintain the ionic balance of the solutions. Let's read the paragraph. We have studied the construction and functioning of the Daniell cell. Daniell cell is using zinc 2 plus as an anode and copper as a cathode. This specific cell is what we call the Daniell cell. This cell has a cell potential of 1.1 volt. This cell converts the chemical energy liberated during the redox reaction being here zinc from 0 going to 2 oxidation state, it is getting oxidized, whereas copper going from 2 plus to 0, it is getting reduced. This is a redox reaction. This cell converts the chemical energy liberated during the redox reaction to electrical energy and has an electrical potential equivalent to 1.1 volt. When concentration of zinc 2 plus and copper 2 plus ions is in unity, such a device is what we call a galvanic or a voltaic cell. Daniell cell is under the galvanic or voltaic cells. If an external opposite potential is applied in the galvanic cell, here an external potential, basically we are connecting a battery, and they describe 3 cases where the E external, the battery, has a voltage of less than 1.1 volt. When that happens, the current flow, where we saw the current flow was from zinc to copper, here as well the current flow will be from zinc to copper, but it will be a little less due to the external potential than the normal one. And the second case, here when the external potential is 1.1 volt, which is exactly equal to the cell potential of the Daniell cell. Here we see that I equals 0, meaning there is no current flow, where the external potential applied is equal to the cell potential. The points in the first case, where E external is less than 1.1 volt, electron flow from zinc rod to copper rod, hence current flows from copper to zinc. Electron will flow from zinc to copper because zinc is the one giving the electrons, and the electrons will flow from zinc to copper, where copper will undergo reduction and gain the electrons and get deposited on the electrode. Hence current flows in the opposite direction of the flow of electrons. So current flows from copper to zinc. Zinc dissolves at anode and copper deposits at cathode. When E external is equal to 1.1, which is equal to the potential of the cell. In such a case, no flow of electrons or current, there is even no chemical reaction. In this, the third case scenario where external E external, the battery connected, has a potential of higher than 1.1 volt. In this case, electrons flow from copper to zinc and current flows from zinc to copper. Zinc is deposited at the zinc electrode and copper dissolves at the copper electrode. In this reaction, we force the reaction to be reversed with an electric potential higher than the cell potential. We saw that in this kind of case, in the normal scenario, zinc with a higher SRP will dissolve in the solution, giving the electrons, and copper will get reduced, depositing on the copper electrode. But when there is a higher external potential than the normal potential, the reaction is reversed. Electrons flow from copper to zinc instead of zinc to copper, and current flows from zinc to copper. Zinc is deposited at the zinc electrode, copper dissolves at the copper electrode. If the external opposite potential is applied in a galvanic cell and increased slowly, we find that the reaction continues to take place till the opposing voltage reaches the value of 1.1 volt. When the reaction stops altogether and no current flows through the cell, any further increase in the external potential again starts the reaction, but in the opposite direction. It now functions as an electrolytic cell. Here we saw that the current is being produced via the reaction and we are getting electricity, but in this there is no electricity, and in this kind of reaction where we are reversing the reaction and we are giving the cell electricity, so it acts as an electrolytic cell in the third case only. A device for using electrolytic cell, a device for using electrical energy to carry non-spontaneous chemical reactions. Both types of cells are quite important, and we shall study some salient features in the following pages. As mentioned earlier, a galvanic cell is an electrochemical cell that converts chemical energy to electrical energy. Chemical energy of a spontaneous redox reaction into electrical energy. In this device, the Gibbs energy of the spontaneous redox reaction is converted into electrical work, which may be used for running a monitor or other electrical gadgets like heater, fan, geyser, etc. The electrical energy we get from the cell, which is basically the reduction in the Gibbs free energy. The chemical energy of a spontaneous redox reaction into electrical energy. This energy is nothing but the Gibbs energy. The Gibbs energy is reduced, electrical energy is produced, which is in the form of electrical work done, which we can use as running a motor, electrical gadgets, heater, fan, geyser, etc. Daniel cell discussed earlier in one such cell in which the following redox reaction occurs. Zinc plus copper 2 plus, zinc will give the electron, copper will get reduced, whereas zinc will give the electrons and zinc will get oxidized. Copper will take the electrons and copper will get reduced. This reaction is a combination of two half reaction whose addition gives this overall cell reaction. This is the overall cell reaction These are the individual half reactions where copper 2 plus is taking electron and becoming copper. This is the reduction half reaction, and zinc solid will dissolve into the solution, giving 2 electrons, which is the oxidation half reaction. This reaction occurs in two different portions of Daniell cell. The reduction half occurs on the copper electrode, while the oxidation half occurs on the zinc electrode. Zinc is getting oxidized, so oxidation half occurs on the zinc electrode, and copper is getting reduced, so the reduction half reaction happens at the copper electrode. These two portions of the cell are called half cells or redox couple. These two, copper and copper 2 plus ion and copper, or zinc and zinc 2 plus ion, these both are two redox couples or two half cells. The copper electrode may be called the reduction half cell and zinc electrode the oxidation half cell. We may construct, based on this kind of model, we can construct a number of cells with various different metals here. As we only need the flow of charges, we can take different types of metals of innumerable pairs and form different kinds of batteries or the galvanic cells in similar model to the Daniell cell. And this is the Daniell cell. We can construct innumerable number of galvanic cells on the pattern of Daniell cell by taking combinations of different half cell. Each half cell consists of a metallic electrode dipped into an electrolyte. For example, in the Daniell cell, we saw that copper electrode is dipped into copper sulfate solution, whereas the zinc electrode is dipped into the zinc sulfate solution. The two half cells are connected by a metallic wire through a voltmeter and a switch externally. The electrolytes of the two half cell are connected internally through a salt bridge. Salt bridge is this one or this one, which will maintain the ionic balance of both the solution. This ionic balance is nothing but, as the zinc will continue to dissolve in the solution, there will be more of zinc 2 plus and the solution will be positively charged compared to the anode or the electrode, which is negatively charged. Here the copper plus from the solution will also be getting reduced and deposited here, which will reduce the copper plus ions concentration in the solution, making the solution negative compared to the electrode, giving the electrode a positive charge, here giving the electrode a negative charge. When this increased concentration of plus charge here in the zinc sulfate solution, because the zinc is getting oxidized, and here the negative charge because most of the copper ions are getting reduced, the reaction will come to a stop. To avoid this, a salt bridge is provided, which will provide the negative ions here and positive ions here to continue the reaction. this is the function and what is the salt bridge. Sometimes both the electrodes in a Daniell cell, we saw that copper electrode was dipped in the copper sulfate solution, whereas zinc electrode was dipped in the zinc sulfate solution. But in some cases, both the electrons dip in the same electrolyte solution, and in such case, we do not require a salt bridge. Why we do not require a salt bridge is because if two electrodes are dipped in the same solution, one electrode is giving the positive charge and one more is giving the negative charge, so it will be balanced. There is no need to provide extra ionic balance or extra oppositely charged ions in this solution, as an anode with negative charge will continue providing plus ions in the solution, whereas the cathode will be getting deposited here and will take off the positive charge from the solution, increasing the negative charge. It will be balanced. At each electrode electrolyte interface, there is a tendency of metal ions from solution. At each electrode electrolyte interface, there is a tendency of metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. Meaning, here copper is getting deposited, copper 2 plus ions from the solution is getting deposited on the electrode, taking the electrons provided by zinc and becoming reduced. This deposit makes the cathode positively charged. At the same time, metal atoms of the electrode have a tendency to go to the solution as ions and leave behind electrons at the electrode, trying to make it negatively charged. In Daniell cell, we see that this is seen in the zinc electrode, where zinc is getting dissolved in the solution and leaving behind electrons. At equilibrium condition, there is a separation of charges, and depending on the tendencies of the two opposing reactions, the electrode may be positively or negatively charged with respect to the solution, and once again with respect to the solution. A third time, the electrode may be positively or negatively charged with respect to the solution. A potential difference develops between the electrode and the electrolyte, which is called electrode potential. When the concentration of all species involved in the half cell is in unity, then the electrode potential is known as standard electrode potential. According to IUPAC convention, standard reduction potentials are now called standard electrode potential. In a galvanic cell, the half cell in which oxidation takes place is called anode, and it has negative potential with respect to the solution. The other half cell in which reduction takes place is called cathode, and it has a positive potential with respect to the solution. Thus, there exists potential difference between the two electrodes, and as soon as switch is on and electrons are let to flow from negative electrode to positive electrode, the direction of the current flows is opposite to that of electron flow. Basically, as we saw here, the zinc is getting oxidized and copper is getting reduced. The potential in which this oxidization takes place is what we call electrode potential. The tendency of zinc on the electrode to get dissolved in the solution is called what we call oxidation electrode potential. And here the tendency of copper 2 plus ions to get deposited on the copper electrode, which is what we call reduction electrode potential. But according to IUPAC convention, we see that standard reduction potentials are only considered. So we do not consider oxidation potentials but only reduction potentials. And as I said before, electrode potential is nothing but reduction electrode potential or standard electrode potential. Electrode potential is nothing but the tendency of the ions to get reduced. In this case, where instead of getting reduced, the zinc is getting oxidized, this electrode potential is said to be negative, whereas here it is positive. And we call this reduction electrode potential as standard electrode potential only when both these concentrations are in unity. And one is occurring a negative standard potential and other having a positive standard electrode potential, there will be a difference in potential which will cause the movement of charges. And one more point they mentioned here is the direction of current flow is opposite to that of electron flow. The potential difference between two electrodes of a galvanic cell is called the cell potential and is measured in volts. The cell potential is the difference between electrode potential, reduction potentials of cathode and anode. It is called the cell electromotive force when there is no current passing through. It is now accepted convention that we keep the anode on the left and the cathode on the right. To remember what is undergoing reaction and what we call a right red cat right side is the place normally we used for cathode representation, and at cathode we see reduction. Cathode is represented the right side, CAT meaning cathode, red meaning reduction, and left an ox. Left representing the left side, anode being represented, and anode we see oxidation. Right red cat, right side cathode, and we see reduction at cathode, and left an ox, left side we see anode, and at anode we see oxidation. And as for the cell potential, the cell potential E cell is nothing but the difference between the standard electrode potential of the individual half cells. Standard electrode potential being the reduction potential of the cells. In here the zinc has a negative reduction potential whereas copper has positive reduction potential. The difference here is nothing but the EMF of the cells, the electromotive force of the cell. While representing the galvanic cell, this is a convention that cathode is on the right and anode on the left. A galvanic cell is generally represented by putting a vertical line between metal and electrolyte solution and putting a double vertical line between the two electrolytes connected by a salt bridge. This is the example. The two electrolytes of Cu and Cu plus with a single vertical line, whereas this is the second, here as well a single vertical line between the electrolytes, but a double vertical line when this is the separation between the two solution. This is a general representation of a galvanic cell. Under this convention, the EMF of this cell is positive and is given by the potential of the half cell on the right hand side minus the potential of the half cell on the left hand side. Half cell on the right is a cathode, or the reduction, where reduction is taking place, and E of the cell on the left is where anode is and where oxidation takes place. The E of the cell is the standard electrode potential on the right side minus the standard electrode potential on the left side. This with an example, cell reaction, Cu is giving 2 electrons, whereas Ag plus, 2 of the Ag plus is taking these 2 electrons to get oxidized, to get reduced. This is reduction. Whereas copper giving the electrons is oxidized. The cathode reaction, cathode right side reduction, so it is getting reduced. Cathode reaction, 2 silver ions taking 2 electrons and becoming 2 Ag solid, getting deposited. Copper taking giving 2 electrons to become copper ion, Cu2 plus ion. It can be seen that the sum of this is 2.5. It can be seen that the sum of 2.5 and 2.6 reaction, which is nothing but the cathode reduction reaction, these both half reactions, will give the overall reaction, this one. In the cell, that silver electrode acts as a cathode and copper electrode acts as an anode. The cell can be represented as follows: E cell, electrode potential of cell, equals E right minus E left, E Ag plus 2 Ag minus E Cu2 plus 2 Cu. Because we are taking only reduction here, where Ag plus is getting reduced and Cu2 plus is getting reduced, is because standard electrode potentials according to IUPAC are only reduction potentials and not oxidation potentials. And one more note point is the potentials of individual cells, individual half cells, for example EAg plus to Ag and or ECU2 plus to Cu cannot be measured. What we can measure is only the E of the cell via connecting a voltmeter to the cell. We cannot measure the individual half reactions here. But the measurement is done via hydrogen, taking hydrogen electrode, which is standard hydrogen electrode, which we take as zero potential and with respect to hydrogen, we find the E of the individual half cells. In the same points, the potential of individual half cell cannot be measured. We can measure only the difference between the two half cell potential that gives the EMF of the cell. If we arbitrarily choose the potential of one electrode half cell, the other can be determined with respect to this. According to the most used convention, a half cell called standard hydrogen electrode, represented by platinum H2 and H+. Platinum acts as an electrode, giving the electrons or acting as a deposition site, is assigned a zero potential at all temperature corresponding to the reaction, either this one H plus getting reduced to become H2 gas, or H2 getting oxidized to produce H plus. The standard hydrogen electrode consists of a platinum electrode coated with platinum black. The electrode is dipped in an acidic solution, because acidic solution is what gives the H plus ions. This H plus ions, with this platinum giving the electrons, will get reduced to give H2. These are the liberated H2 gas bubbles. The electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. The concentration of both the reduced and the oxidized form of hydrogen is maintained at unity. This figure. This implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. At 298 Kelvin, the EMF of the standard hydrogen electrode second half cell and the second half cell constructed by taking a standard hydrogen electrode as an anode and other half cell as cathode gives the reduction potential of the other half cell. If the concentrations of oxidized and the reduced forms or species in the right hand half cell are in unity, the cell potential is equal to standard electrode potential of the half cell. So, since we can't find out individual electrode potentials. For example, this one, if we take, we cannot find EAG plus to AG individually. We can only find E cell. As such, we take a standard hydrogen electrode as a convention, where we take this as 0 volt of electrode potential, where we know if we know E cell, we can know the E cell, and we can know the standard hydrogen electrode, which we take as 0 minus whatever we want to find. We will get the value of this as equal to the negative of the cell or positive, depending on what you are taking. This will give the individual, and this reduction potential or standard potential is only with respect to hydrogen. The concentration of the oxidized and reduced form, and this E0 is a value where we take that the second species we take, if the species we want to find, for example AG, should this E naught represents the electrode potential of Ag when the oxidized and reduced forms are in unity. The concentrations are in unity. E naught representing unity of the concentration of oxidized and reduction forms. As the electrode potential for standard hydrogen electrode is 0, the electrode potential of the cell for in this case will become equal to the electrode potential of the right hand side, which is the cathode. The measured EMF of the cell, platinum as an electrode and H2 gas to hydrogen getting oxidized to form H plus ions, and another solution of copper 2 plus gaining electrons getting reduced is 0.34 volt, meaning since the total E standard of the cell is 0.34 volt, and we take hydrogen as 0, so the electrode potential of copper Cu2 plus to Cu will become 0.34 volt. Cu2 plus 2 electrons, the copper is reduced and deposited on the electrode. Similarly, the measured EMF of the cell, platinum H2S and zinc Zn2 plus zinc. In this reaction, we took one electrode as hydrogen, where hydrogen is providing the electrons and copper is getting reduced. In this reaction, this one, hydrogen gives electrons and copper takes electrons, meaning copper has higher electrode potential compared to hydrogen, meaning copper can be more easily reduced than hydrogen compared to hydrogen. As such, when competing with hydrogen for the electrons, copper will easily take the electrons and will have a positive, meaning higher than 0, higher than hydrogen potential. So copper is easily reduced. But in this reaction, if we see, hydrogen will take the electrons, whereas zinc will give the electrons. This indicates that hydrogen is more easily reducible, meaning easily gain electrons, than zinc to gain electrons. That is why the value here, the value of the standard electrode potential is negative 0.7 volt. Zinc 2 plus. Basically, the value here is positive because copper can more easily take the electron than hydrogen, but here the value is negative because hydrogen can take the electron more easily than zinc. The positive value of the standard electrode potential in the first case, the copper and hydrogen case, indicates that copper Cu2 plus ion get reduced more easily than hydrogen plus ions. The reverse process cannot occur, that is, hydrogen ions cannot oxidize Cu, or alternately we can say that hydrogen gas can reduce copper ion, which means hydrogen will give electrons to the copper ion. Under the standard conditions described above, thus copper does not dissolve in HCl. Copper, a solution, copper if we add, copper will stay like this, it will not dissolve in the solution because normal hydrogen is not able to take electrons from copper and make it into Cu2 plus aqueous state. Because we saw that hydrogen is less reducible than copper and copper can easily take electrons more than hydrogen, having a positive electrode potential value, while hydrogen only has 0. But when we take a case, this is a HCl solution, and when we take a HCl solution but take zinc, we can see that zinc can dissolve. This happens because zinc, as we see in this equation, zinc can easily give electrons becoming into a zinc 2 plus aqueous state, dissolving into the solution, where hydrogen will take the electrons and get liberated to form H2 gas. But copper cannot, because copper is more reducible than hydrogen. As such, when we throw copper into a solution of HCl, we don't see any kind of bubbles forming. But when we throw zinc, we see that hydrogen gas is liberated. And one more case where if we throw copper into a solution of nitric acid, the representation I am drawing here doesn't mean metals can float on solution, it is just a representation. HNO3, which is the nitric acid, here copper can indeed dissolve, but this is not because H plus is taking electrons from the copper, but it is due to the reaction between NO3 and copper. NO3 being very strong, it can react with copper. This is what reaction which causes the dissolving of copper in a HNO3 solution, which is a nitric acid solution. In nitric acid, it is oxidized by nitrate ion. Oxidized meaning the nitrate ion will come to the copper and take the electrons, and not by hydrogen ion. The negative value of the standard electrode potential in the second case indicates that hydrogen ions can oxidize zinc, or zinc can reduce hydrogen ions, because zinc has a negative 0.76 volt value. Hydrogen is more reducible than zinc. In view of this convention, the half reaction for Daniell cell in Fig 2.1 can be written as this one. Left electrode where zinc will give the electrons, right electrode where copper will take the electrons and get reduced. The overall reaction of the sum of the two reactions is this one. The EMF of the cell 0.34 volt with respect to hydrogen is the right side, the cathode side, the electrode potential, and minus negative 0.76, which is the electrode potential of zinc. If minus into minus plus 0.34 plus 0.76 will give us a value of 1.1 volt for the Daniell cell. Sometimes metals like platinum or gold are used as inert electrodes. As we see here, this one is a platinum electrode, is used here as inert electrodes. They do not participate in the reaction but provide their surface for oxidation or reduction reactions and for the conduction of electrons. For example, platinum is used in the following half reaction: hydrogen electrode, platinum H2G vertical and H plus aqueous. This is the standard electrode potential. Standard hydrogen electrode SHE, which has a 0 volt potential, assuming with half cell H plus getting reduced to form H2 gas. And another example is bromine electrode, platinum bromine, with the half cell reaction, bromine getting reduced again. We're going from 0 here to -1, getting reduced. The standard electrode potentials are very important and we can extract a lot of useful information from them. The values of standard electrode potentials for some half cells are given in the table 2.1. Here we see that this is the table. We see that F2 plus 2 plus giving 2F minus ion getting reduced has a electrode potential of 2.87 volt, which is the highest we see in this table. We can understand by this that the tendency for fluorine gas to accept electrons to become fluorine ions is really high. So we can assume, as fluorine is getting reduced, we can assume that fluorine is a really strong oxidizing agent. As fluorine has a high tendency to get reduced, fluorine is a really strong oxidizing agent, as it can take the electrons getting reduced by itself. And the least value or the most negative value being -3 from lithium, meaning that lithium ion cannot take this E minus with the very easily, being the least easily in this table, meaning lithium ion can easily give one electron and become lithium plus ion, but it has the hardest or the least tendency for lithium to get reduced by taking an electron and becoming lithium metal. So we can call lithium metal to be a really strong reducing agent as it is undergoing oxidation, whereas fluorine to be a really strong oxidizing agent as it is getting reduced. If the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable compared to hydrogen gas. Basically, here this 2F minus, which is the reduced form, is really stable. That is the reason the tendency to undergo reduction in fluorine is very high, of the 2.87 volt. But we can understand as a tendency to undergo reduction in lithium plus ion is very less, that lithium solid is very unstable compared to the hydrogen ion, which has a 0, very unstable compared to the hydrogen gas. So as such, it can be very stable in the lithium plus. Similarly, if the standard electrode potential is negative, let me read again. If the standard electron potential of an electrode is greater than 0, being positive, then its reduced form, the element's reduced form, is far more stable compared to hydrogen gas. As we see in fluorine, as it is positive, is the F minus ion is more stable than H2 gas. Similarly, if the standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the species. It can be seen that the standard electrode potential of fluorine is the highest in the table, indicating that fluorine gas has the maximum tendency to get reduced to fluoride ions, and therefore fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent, as it cannot go on oxidation. Lithium has the lowest electrode potential, indicating its lithium ion is the weakest oxidizing agent where it cannot undergo reduction, while lithium metal is the most powerful reducing agent in an aqueous solution, as it can easily give off an electron. It may be seen that as we go from top to bottom in the table, standard electrode potential decreases with this, decreases the oxidizing power of the species, reducing power. Electrochemical cells are the uses of the electrochemical cells are given here, are extensively used. Electrochemical cells are extensively used for determining the pH of solutions, the solubility product, equilibrium constant, and other thermodynamic properties, and for potentiometric titrations. The uses being electrochemical cells are used for determination of pH of solution, solubility product, equilibrium constant, thermodynamic properties, potentiometric titrations. In text question, how would you determine the standard electrode potential of the system Mg2 plus and Mg? The standard electrode potential being when the oxidized and reduced forms being in unity, we can take the total cell potential from the Mg2 plus to Mg cathode and hydrogen as the standard hydrogen electrode, and we can find the potential electrode potential of Mg2 plus from the cell, taking the standard hydrogen electrode as 0. Can you store copper sulfate solutions in a zinc pot? No. Why? Because we saw before that copper can easily take electrons even more better than hydrogen. Cu2 plus can easily take electrons even more better than hydrogen. As such, having a positive electrode potential value. But we see that zinc 2 plus cannot take electrons very easily and even has a negative value, a negative 0.74 volt value, meaning it is very weak compared to hydrogen and copper in terms of reduction potential. So if you store copper sulfate solutions which has Cu2 plus ions in a zinc pot, the copper 2 plus will react with the zinc giving the 2 plus giving the electrons and dissolving in the solution, the reaction being Cu2 plus zinc giving Cu. Copper will be deposited in the sides and zinc will be dissolved in the solution. There will be a displacement reaction where the copper sulfate solution the copper in the copper sulfate solution will be displaced by zinc and copper will be deposited. As such, we cannot store such reactive copper sulfate in a zinc pot, and suggest three substances can oxidize. Consult the table of standard electrode potential and suggest three substances that can oxidize: ferrous ion Fe2 plus ion, Fe2 plus to Fe3 plus. For oxidation, we need help of an oxidizing agent. Oxidizing agent needs to undergo reduction very easily, so we need substances which can easily undergo reduction, meaning have high standard electrode potential. So we need to reduce Fe2 plus into Fe3 plus electron. We need substances with high electrode potential, which can be peroxide, which has 1.78, cobalt 3 plus into cobalt 2 plus, permanganate, dichromate, etc., having a really high potential, standard electrode potential compared to iron or ferric ion. We have assumed this is the Nernst equation. The second topic we will be studying. We have assumed in the previous section that the concentration of all the species involved in the electrode reaction is in unity. That is why we call it as standard electrode potential, represented by E0. This is when the concentrations are in unity. But that is not always the case, as it is not always seen that in realistic situation there is no unity. This need not be always true. Nernst showed that for the electrode reaction, metal with some charge plus electrons will turn into, this is the reduction half reaction. The electrode potential at any concentration measured with respect to standard hydrogen electrode can be represented by E0 being the standard electrode potential and E being when there is no unity. E, the electrode potential, equals standard electrode potential minus RT, R being the gas constant, T being temperature, N being the number of electrons, and F being Faraday's constant, times ln of metal concentration by metal ion concentration. This is the main equation, or what we call the Nernst equation. But concentration of solid, basic form of the Nernst equation. But concentration of solid metal, solid M metal, is taken as unity, and we have this equation. E standard has already been defined. R is gas constant, F is Faraday constant having 96,487 Coulomb per mole, T is temperature in Kelvin, and Mn plus is a concentration of species or metallic ions. This is a standard electrode potential chart or table which we saw. We see that as we go down the table, the standard electrode potential goes on decreasing with fluoride, cobalt 3 plus, hydrogen peroxide, permanganate, gold, with gold being a really high, actually not really high, but somewhat high reduction potential, because we do not see gold ions. We only see gold. Gold is unreactive because this form being very stable compared to the ionic forms, and Cl2 we see that they exist in chloride ions, oxygen, MnO2, etc., and with the lower forms being H2O. H2O we see that normally H2O doesn't exist in the form of H2O but in the form of H2 and 2OH minus. The H2 this having a negative potential, meaning this form is less stable than this form. So these this is not normally seen, as if seen in such a form this will be oxidized to give H2O plus electron. A negative E naught means, or standard electrode potential means, that redox couple or reaction half cell is a stronger reducing agent than H plus couple, meaning it is a higher it has higher oxidation power than the H plus H2 couple. A positive E naught means that the redox couple is a weaker reducing agent than the H plus H2 couple, but being a stronger reducing power. Positive value means they can easily be reduced, acting as strong oxidizing agents. In Daniell cell, the electrode potential of any given concentration of Cu2 plus we write for cathode. This is the first half cell reaction. We are taking cathode, or E right red cat, right side cathode reduction based on standard convention. This is the E half cell where we take from E Cu2 plus to Cu when this is the electrode potential not in unity, and this is standard when the concentrations are in unity, minus this value should be, as we know, 0.34 minus RT by, as we see that copper 2 plus is getting reduced to copper, the transfer is of 2 electrons. So we took 2 here, RT by 2F ln of, as we see that we are taking this as 1 by, this is the concentration of the Cu2 plus ions in the aqueous solution. This is the second half reaction, E left this taking is, as it's a standard electrode potential according to IUPAC, it's a reduction potential, so zinc 2 plus getting reduced to zinc. This will be a value, as you remember, 0.7 something, 0.76, and here as well there is a transfer of 2 electrons, so we take 2 here, and the cell potential being E right minus E left, or E cathode minus E anode, we substitute the equation, and here we see that we get this equation. Here we see the formula ln A minus ln B equals ln A by B. Using this formula we get this equation. It can be seen that E cell depends on the E concentration of both, because here we have both zinc concentration as well as copper concentration, both Cu2 plus and zinc 2 plus ions. It increases with the increase in the concentration of Cu2 plus ions and decreases in the concentration of zinc 2 plus ions. by converting the natural logarithm in equation 2.11, this is a ln, to base of 10 and substituting the values of R, F and T. T we take it as 298 Kelvin. It reduces to E cell equals 0.059 by 2 log zinc 2 plus concentration by Cu2 plus concentration. We should use the same number of electrons N for both the electrodes and thus the following cell. In example here we see that both in this kind of reaction we see that copper is also getting reduced via 2 electrons and zinc is also getting reduced via 2 electrons. So we take 2F. But what if in this kind of case, in this case where nickel needs 2 electrons whereas silver only needs 1 electron. Here we take 2 Ag. 1 Ag plus taking 1 electron, 2 Ag plus will take 2 electrons. So we can substitute 2 here. As for the concentration case, we square the single Ag plus concentration. By squaring, we will get the accurate value. And for a general electrochemical reaction of type small a, which small a, small b, small c and small d being the coefficients and the capital letters being the actual elements, Nernst equation can be written as E cell equals E naught cell RT by NF ln Q, where Q is the concentration of product of concentrations in the power of their coefficients by the product of the concentrations in the power concentration of reactants in the power of their coefficients. This is what we get E cell from. The potential of the cell when there is no unity between the oxidized and the reduced concentrations. This is an example. Represent the cell in which following the reaction takes place: Mg plus 2Ag plus and Mg2 plus to 2Ag. Here we see that Mg is the one getting oxidized, giving the electron, so it is at the anode which is getting oxidized, and 2Ag plus taking the 2 electrons is getting reduced to form. And they gave that we should calculate E of the cell, where they gave the concentration as 10 power 0.1 in 10 power minus 4 molar concentration for Ag plus and 0.13 molar concentration of Mg2 plus, and they gave that the standard electrode potential of the cell is 3.17 volt, and this is the standard representation. And using the Nernst equation we can see that E cell equals, if we substitute the value in this equation, we get the value is approximately equal to 2.96 volt. Equilibrium constant from Nernst equation we can derive. We saw that in the earlier pages we saw that the electrochemical cells are extensively used for determining pH solubility and equilibrium constant. That is the current derivation we are going to do. Equilibrium constant from Nernst equation. In the circuit, in the Daniell cell, the first diagram is closed, current is flowing. Then we note that the reaction zinc plus Cu2 plus going to zinc 2 plus copper takes place, and as time passes the concentration of zinc 2 plus keeps on increasing while the concentration of Cu2 plus keeps on decreasing. At the same time, voltage of the cell as read on the voltmeter keeps on decreasing. After some time, we shall note that there is no change in the concentration of Cu2 plus and zinc 2 plus ions, and at the same time voltmeter gives 0 reading. This indicates that equilibrium has been attained. In this situation, the Nernst equation may be written. Nernst equation can only be written after the equation has reached equilibrium, has attained equilibrium. E cell, because the voltage will reach 0 when the reaction stops, the current flow will stop. When I equals 0, potential is also 0. That is when equilibrium is attained. In this case, E cell is 0 equals E standard of the cell minus 2.303 RT by 2F log zinc 2 plus by copper 2 plus. Or we take the minus sign to this side, which will become positive. At equilibrium, we see that the concentration of zinc ions by concentration of copper 2 plus ions will be Kc, which is the equilibrium constant, because zinc 2 plus is a product and Cu2 plus is the reactant. Zinc 2 plus is formed, and and in the previous class we learned that Kc equals product, the concentration of the product of the products times by the product of the concentrations of the reactants. Whole to the power of their coefficients. The same reason we see that this will be Kc, as the equation has attained equilibrium. Kc for the reaction will be concentration of the zinc ions by concentration of the copper ions. At a temperature of 298 Kelvin, the above equation can be written as the standard electrode potential of the cell equals 0.059 volt by 2 log of Kc, because the log of the zinc ions by copper ions, which is equal to Kc for at equilibrium, so the log of Kc, and we know the standard electrode potential of the cell, which is 1.1 volt. For finding out Kc, we can shift this to that side, and log Kc will be equal to approximately 37.288, and Kc will be equal to 2 into 10 power 37 at 298 Kelvin. This is a really big Kc. The standard electrode potential is equals 2.303 gas constant times temperature in Kelvin by the number of electrons shared or gained times Faraday's constant into log of Kc. Thus equation 2.41, or basically this equation, gives us a relationship between equilibrium constant of the reaction and standard electrode potential of the cell in which that reaction takes place. Thus, equilibrium constant of the reaction, difficult to measure otherwise, can be calculated from corresponding standard electrode potential value of the cell. That is the reason we use electrochemical cells. One of the use is finding out the equilibrium constant. This is one of an example. Calculate the equilibrium constant of the reaction. Cus plus 2Ag plus gives Cu2 plus 2Ag. The standard electrode potential of the cell given as 0.46 volt. Substitute in this equation. In the above equation, where we get E standard cell as this 0.46 and 0.46, we will get a Kc, an approximate value, the equilibrium constant being 3.29 into 10 power 15. The next one being electrochemical cell and Gibbs energy of the reaction. And on the first pages of the chapter, we read that galvanic cells convert chemical energy into electrical energy. This electrical energy, more specifically, is attained or gained from the spontaneous reactions of the chemicals. This spontaneous reactions providing energy is deducted from the Gibbs energy. Now, how much Gibbs energy is reduced or the change in Gibbs energy is the relation between electrochemical cell and the Gibbs energy of reaction. Basically, electrical work done in 1 second is equal to the electrical potential multiplied by total charge. This is the basic definition of the voltage or potential. V equals W by Q, whereas electrical work done equals QV, which is the charge times the potential. Work done in 1 second is equal to the electrical potential multiplied by total charge passed. If we want to obtain maximum work from a galvanic cell, then the charge has to be passed reversibly. The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy, and therefore reversible meaning nothing but a slowly. It should not happen. If we want to obtain maximum work done, we should not obtain in a very fast way, but in a reversible and slow way. Reversible is another way of saying the reaction should happen in many steps being very slow. You should continuously provide us energy, attributing to the reduce in the Gibbs energy. If you want to obtain maximum work done from a galvanic cell, then the charge has to be passed reversibly. The reversible work done by galvanic cell is equal to the decrease in its Gibbs energy, and therefore if the EMF of the cell is E and NF is the amount of charge passed, and delta RG is the Gibbs energy of the reaction, then delta RG, the reduction Gibbs free energy reduction, is equal to the negative times NF times E, where E is the EMF of the cell and MF is the amount of the charge passed. It may be remembered that E cell is an intensive parameter, but the G delta reduction G or Gibbs energy is an extensive thermodynamic property, and value depends on number. The more the number of the atoms or the elements, or molecules or substance, the more the amount of the G value. Basically, we see that for no matter the amount of substance we take, for a Daniell cell, the cell potential is always 1.1 volt. It doesn't matter if it will hold for 1 second or 2 seconds or many hours, but the final E cell value will only be 1.1. That is why we call it as intensive property. But Gibbs reduction energy will depend on the amount of substance. If more the substance, more the amount of Gibbs energy produced, or Gibbs energy changed. More the substance, more the amount of Gibbs energy changed. That is what they are saying, is a thermodynamic property, and the value of depends on n, the number. Thus we can take an example: zinc plus copper 2 plus gives zinc 2 plus copper, and delta Rg equals -2. But if we take 2 molecules of each, the number is twice and we get -4 Fe as the value. If the concentration of all the reacting species is in unity, meaning all the concentration is same, then E cell equals E standard cell. So standard electrode potential, and we can substitute in the place of E cell, we can substitute E standard of cell, which is, for example, in the Daniell cell being 1.1 volt, which is E standard. Thus, from measurement of E standard of cell, we can obtain an important thermodynamic quantity, which is the reduction in Gibbs energy, standard Gibbs energy of the reaction. From the later we can calculate the equilibrium constant by the equation, which is this equation. An example given: the standard electrode potential for a Daniell cell is 1.1 volt. Calculate the standard Gibbs energy for the reaction. Gibbs energy is nothing but -n into Faraday's constant into the electron in standard electrode potential. N in the above equation is 2 because 2 electrons is there. Zinc is giving 2 electrons, copper is gaining 2 electrons. Faraday constant value being a constant and this being 1.1 volt, we will get the answer to be 212.27 kilojoule per mole. This is the standard Gibbs energy. Calculate the potential of hydrogen in contact. In text question, calculate the potential of hydrogen electrode in contact with a solution whose pH is 10. Calculate the EM of the cell in which the following reaction takes place: Ni plus 2Ag giving Ni2 plus. We can substitute this in the above equations to get the answer. The cell in which the following reaction occurs. Calculate the standard Gibbs energy and equilibrium constant of the cell reaction. We can calculate in this equation, from this equation. And the next topic, conductance of electrolytic solutions. And before that, it is necessary to define a few terms. Consider the subject of conductance of electricity through electrolytic solutions. The electrical resistance is represented by the symbol R and is measured in ohm, represented by omega, which is in terms of SI unit is equal to kg meter square per Simon cube A square. It can be measured with the help of a Wheatstone bridge which you are familiar with. Of course, you are familiar with in the study of physics, third chapter, current electricity. The electrical resistance of any object is directly proportional to its length and inversely proportional to its area of cross section. Basically, resistance equals rho L by A, meaning resistance is directly proportional to L by A, directly proportional to L. As length increases, resistance also increases. As area of cross section increases, resistance will decrease, inverse proportionality. And the resistance SI unit is ohms, and ohms is represented by a symbol of omega. In terms of SI base units, it is equivalent to kg meter square per Simon cube A square. It can be measured with the help of unknown resistance, can be measured with the help of Wheatstone bridge. The constant of proportionality here, R is proportional to L by A, and to remove this proportionality we multiplied R with a constant rho, which we can either call specific resistance or resistivity. The constant of proportionality rho is called resistivity or specific resistance. Its SI unit are ohm meter, and quite often its submultiple ohm centimeter is also used. IUPAC recommends the use of the terms resistivity over specific resistance, and hence in the rest of the book we shall use the term resistivity. Physically, the resistivity for a substance is its resistance, and when it's 1 meter long and area of the cross section is 1 meter square. Resistance equals rho L by A, and when L equals 1 meter, A equals 1 meter square, it is 1 by 1 into rho equals R. When L, in this condition, R is equal to rho. This convention or conversion, 1 ohm meter, which is the SI unit of resistivity, is equal to 100 ohm centimeter, or 1 ohm centimeter equals 0.01 or into or 10 power minus 2 ohm meter. The inverse of resistance is called R, is called conductance, G, and we have the relation G equals 1 by R or A by rho L equals kappa into A by L. The SI unit of conductance is Siemens, represented by the symbol S, and is equal to ohm inverse, also known as mho or omega inverse. The inverse of resistivity, called conductivity, specific conductance, is represented by the symbol kappa, which is K or small k, or which is a Greek kappa. IUPAC has recommended the use of the term conductivity over specific conductance, and hence we shall use the term conductivity in the rest of the book. The SI units of conductivity are Simon per meter or Simon per centimeter. Conductivity is of a material in its conductor. Basically, conductance represented by G is 1 by resistance, and kappa, conductivity, is 1 by resistivity. The SI unit for conductance being Simon or ohm inverse, Simon represented by S, and for kappa conductivity being Simon meter inverse and G is equal to conductivity, conductance is equal to conductivity when the area is 1 meter square along with length being 1 meter. Conductivity of a material in Simon per meter is its conductance when it is 1 meter long and its area of cross section is 1 meter square. It may be noted that 1 Simon centimeter inverse equal to 100 Simon meter inverse. These are some values. The values of conductivity of some selected materials at a temperature of 298.15 Kelvin, which is the room temperature. Sodium, we see that the conductivity is somewhere in the 2100 Simon per meter, copper being 5.9 and silver being 6.2 into 10 power 3, which is 6200 Simon per meter, being the highest conductivity here. And as for insulator, we see that glass has a 10 power minus 16 conductivity, whereas Teflon has 10 power minus 18. And for aqueous solution, pure water has a really low conductivity, whereas a solution of 0.1 molar HCl has a conductivity of approximately 4. A 0.01 molar KCl has a conductivity of approximately 0.14, etc. Semiconductors of cupric oxide has 1 into 10 power minus 7, whereas silicon has 10 power minus 2 range, and germanium has 2 Simon per meter of conductivity. It can be seen that at table 2.2 the magnitude of conductivity varies a great deal and depends on the nature of the material. Here we see that in conductors we see a really high conductivity, whereas insulators are really low conductivity, and aqueous solutions we see that except pure water the other solutions have a somewhat medium conductivity, whereas semiconductors vary more. Is also this conductivity depends it depends on the nature of the material, being conductors, insulators, semiconductors, aqueous solutions, etc. Second, on the temperature. Here in this table we see that it is taken at room temperature. It depends on temperature and pressure at which the measurements are made. Materials are classified into conductors, insulators and semiconductors depending on the magnitude of their conductivity. Metals and their alloys have very large conductivity and are known as conductors. Certain non-metals like carbon black, graphite and some organic polymers are also electronically conducting. Substances like glass, ceramic, etc. having very low conductivity are known as insulators. Substances like silicon, doped silicon and gallium arsenide having conductivity between conductors and insulators are called semiconductors and are important electronic materials. Certain materials called superconductors by definition have zero resistivity, rho being 0, or kappa being infinity. These kind of conditions are seen in superconductors. By definition have zero resistivity or infinite conductivity. During the early ages, only metals and their alloys at extremely low temperatures of 0 to 15 Kelvin were known to behave as superconductors, but now a number of ceramic materials and mixed oxides are known to show superconductivity at temperatures as high as 150 Kelvin. Electrical conductance to metals or electrical conductance to metals is called metallic or electronic conductance and is due to the movement of electrons. The electronic conductance depends on nature and structure of metal, number of valence electron per atom, temperature. It decreases with increase of temperature. Basically, in a metal conductor, the conductance is due to the flow of electron. This is what we call electric conductance, and this primarily depends on nature and structure, lattice arrangement of the metal or nature of metal. The more number of electrons, the more the charge or the more the flow of charge and more the current or electrical conductance. Temperature. The temperature is inversely proportional to conductivity. Higher the temperature, lower the conductance. Here they gave something about polymers, non-metals like carbon, graphite, and some organic polymers. As we see that normally non-metals are normally non-conductors or insulators, but some non-metals like carbon black, graphite, and some organic polymers. This organic polymers, they gave an explanation. Electronically conducting polymers. In 1977, Magd, Diarmid, Heger, and Shirakawa discovered that acetylene gas, which is the C2H2 gas or the ethane gas, can be polymerized to produce a polymer. Polyacetylene, when exposed to vapors of iodine, acquires metallic luster and conductivity. Since several organic conducting polymers have been made, such as polyaniline, polypyrrole, polythiophene, these organic polymers, which have properties like metals, being wholly composed of elements like carbon, hydrogen, and occasionally nitrogen, oxygen, or sulfur, are much lighter than normal metals and can be used for making lightweight batteries. Besides, they have mechanical properties of polymers such as flexibility, so that one can make electronic devices such as transistors that can bend like a sheet of plastic. For discovery of conducting polymers, Magd, Diarmid, Heger, and Shirakawa were awarded the Nobel Prize of Chemistry for the year of 2000. Basically, when these three scientists invented that when the C2H2 acetylene gas is polymerized and exposed to vapors of iodine, it attains metal-like properties. Metal-like properties along with conductivity. Such kind of things are not only possible with the acetylene gas but can be possible with polyaniline, polypriol, and polythiophene. And these uses can be used in making transistors, lightweight batteries, etc. As they are conductive, they can be used very much. And because they are made of carbon, nitrogen, oxygen, or sulfur kind of compounds, they can be easily used for making lightweight batteries. Mechanical properties of polymers, and because they are polymers consisting of chains of single units of monomers, and they have flexibility. Yes, that is the explanation of electrically conducting polymers or organic polymers, which as to how even non-conductors or non-metals can conduct electricity in some cases. And as for electrical conductance through metals is called metallic or electronic conductance, and is due to the movement of electrons. Metal movement of electrons is what we call electricity, and it depends on nature and structure of the metal, the number of valence electrons per atom, the temperature. Is inversely proportional to temperature. As electrons enter at one end and go out through the other end, the composition of the metallic conductor remains unchanged. The mechanism of conductance through semiconductors is more complex. We already know that very pure water has small amounts of hydrogen and hydroxyl groups, which is approximately 10 power minus 7 molar concentration, which lend it very low conductivity, which we saw here in the above table, which is of 3.5 into 10 power minus 5. When electrolytes are dissolved in water, they furnish their own ions in the solution, hence its conductivity also increases. The conductance of electricity by ions present in the solution is called electrolytic or ionic conductance. Before, when the conduction or electrical conduction through metals is what we call electrical conductance, but in solutions through ions, when ions furnish the solution, it is called ionic or electrolytic conductance. This depends on the nature of the electrolyte added, size of ions produced and their solution, the nature of solvent and its viscosity, concentration of the electrolyte, temperature. Here we see that the ionic conductance is directly proportional to temperature, whereas the metallic conductance is inversely proportional to temperature. And the problems we face in the ionic conductors is that passage of direct current through the ionic solution for a prolonged period can lead to changes in the composition due to the electrochemical reactions. In the electrochemical cells, we saw about electrolytic cells which utilize energy to undergo non-spontaneous reactions. As such, instead of passing the electricity like metals do, when we pass direct current, these solutions will undergo non-spontaneous reactions. This will lead to change in the composition of the solution. We know that accurate measurement of unknown resistance can be performed on a Wheatstone bridge. However, for measuring the resistance of an ionic solution, we face two problems. Firstly, passing the direct current changes the composition of the solution. Secondly, a solution cannot be connected to the bridge like a metallic wire or a solid conductor. The first difficulty is resolved by using an alternating current AC source of power via an oscillator. The second problem is solved by using a specially designed vessel called conductivity cell. These are the examples for conductivity cells. It is available several designs and two simple ones are shown in the figure below. This is the solution you want to find the conductivity for, and these are the platinized electrodes, and these are the connecting wires. These are two different types of conductivity cells. For finding the resistance of the unknown solution, we use special cells which we call the conductivity cells, and two of the simple ones are here. Basically, they are defining the conductivity cell here. Basically, it consists of two platinum electrodes coated with platinum black. Finely divided metallic platinum is deposited on the electrodes electrochemically. These have area of cross section equal to A and are separated by a distance L. Therefore, solution confined between these electrodes is a column of length L and area of cross section A. The resistance of column of solution is then given by the equation. R equals rho L by A. We know that resistance equals rho L by A, which is the basic formula, and rho equals 1 by conductivity. As such, this formula is found out. The quantity L by A, which is length by area, is called cell constant. As we see here, the conductivity cell, the length and area can be considered a constant denoted by the symbol G star. It depends, this quantity G star depends on the distance between the cells, electrodes, and their area of cross section. As G cell is defined by L by A, it depends on the distance between the electrodes as well as the area of the cross section of the electrodes. Has the dimension of length inverse and can be calculated if we know L and A. Measurement of L and A is not only inconvenient but also unreliable. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. What they are saying is measuring the length and area of cross section for conductivity cells or for the apparatus is very inconvenient and many errors can be found. As such, using this formula, where we already know the conductance of a specific solution, we use the conductance to find G star. We can write R equals rho G star, or resistance equals G star by K, or kappa, or conductivity. Via these formulas, we can find out G star without the need for physical usage of measurement. For this purpose, we generally use KCl solution whose conductivity is known accurately at various concentrations. So what solution we can, basically for finding out the G star value, we use KCl solution, which we know the conductivity accurately. Table 2.3, they gave concentration, molarity, conductivity and molar conductivity values. Of concentration 1, the conductivity is 0. This is the for KCl values. This is specifically only for KCl solution. These are the values. We can say that KCl here is actually, we can take it as a test solution for finding the G star values. And at different temperature, as we know that the conductivity, molar conductivity will change according to temperature. At different temperatures, they have given the values of KCl solutions. The cell constant G star is then given by the equation G equals L by A R into kappa. This is the equation. They just shifted the conductivity this side, so RK equals G star, which we have a constant value. After finding this with KCl solution, which we know the K conductivity values very accurately, after finding the G star value, we can replace the KCl solution with other solution, and we already have the G star solution value, G star constant value. So then we can find the unknown conductivity. Once the G star or cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup for the measurement of the resistance is shown in the figure 2.5. This one, they took a Wheatstone bridge. This is an oscillator which is providing the current, or the AC source, because DC source will, with prolonged exposure, will change the composition of the solution, and oscillator will provide AC current. AC current, this is the bridge where R4 and R3 and R4 are fixed, and R1 is a rheostat, meaning it's a variable resistant. Rheostat, variable resistance. As we continue to change the resistance here, and when the balanced condition, when R2 by R4 equals R1 by R3, if such a condition arrives, the detector here will show zero deflection, meaning the current here will be zero. As we continue to change the ratio, when the ratio is equal, and when we find that there is zero current passing through this value, then this branch, then we can find R2 equals R4 R1 by R3. This is how we find the value of the conductivity cell of the solution. This is a conductivity cell. It consists, that basically defining the diagram here, consists of two resistances R3 and R4, a variable resistance R1, and a conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by an oscillator, a source of AC power in the audio frequency range 550 to 5000 cycles per second. P is a suitable detector, a headphone or other electronic devices, and the bridge is balanced when no current passes through the detector. Under the conditions, when the Current passing through this branch will become 0. Unknown resistance is this formula. These days, inexpensive conductivity meters are available, meaning less cost conductivity meters are available, which can directly read the conductance or resistance of the solution in the conductivity cell on the cell constant, and the resistance of the solution in the cell is determined. The conductivity of the solution is given by the equation C cell constant by R, G star by R. We know the equation that R equals rho L by A and R equals L by A kappa, and we know that L by A is G star, so R equals G star by kappa and with this G star is also called the cell constant, and if you want the conductivity value, kappa equals G star by resistance. The conductivity of solution of different electrolytes in the same solvent and at given temperature differs due to charge and size of ions in which they dissociate. The concentration of ions or ease with which ions move under a potential gradient, it therefore becomes necessary to define a physically more meaningful quantity called molar conductivity, denoted by symbol lambda m, Greek lambda. It is related to conductivity of the solution by the equation molar conductivity equals conductivity per concentration, per unit concentration. So let me read it, the sentence. The conductivity of solutions of different electrolytes in same solvent and at given temperature differs due to charge. Basically what they are saying is, at a given solution, if we take different, this is a conductivity cell, this cell has a solution, and this solution has, if there is a kind of ions, there are two types of ions, A ions and B ions. The first case, the first conductivity cell has A ions and second conductivity cell has B ions in the solution. Both have different conductivity. This may be due to this change in conductivity may be due to charge change, difference in charge, or size of the ions in which they dissociate. It may be one. This difference in conductivity may be due to charge difference, two, dissociation rate, how much they dissociate. Third, concentration. Or fourth one, the ease with which the ions move under the potential gradient, the easy moving ability or mobility of the ions. to define such terms, as we already found out that it depends on the concentration, instead of writing every time, they define a physically more meaningful quantity called molar conductivity. It is denoted by lambda m. It is related to the conductivity of solution by lambda m. Lambda m equals conductivity by concentration, or unit conductivity per unit concentration. In the above equation, if kappa is expressed in Simon per meter and the concentration C in mole per meter cube, then the unit of lambda m are Simon meter square per mole. It may be noted that 1 mole meter cube equals 1000 liter per meter cube into molarity mole per liter, and hence lambda m equals conductivity by 1000 liter meter per meter cube into molarity. If we use Simon per centimeter as the unit for conductivity and mole per centimeter cube, the units as the units of concentration, yes. If we use Simon per centimeter as a unit for conductivity and concentration as mole per centimeter cube, the units of concentration, then units for lambda m are Simon centimeter square per mole. It can be calculated by using the equation conductivity times 1000 concentration by molarity. Both types of units are used in literature and are related to other by equations. 1 Simon meter square per mole equals 10 power 4 Simon centimeter square per mole. 1 Simon centimeter square per mole equals 10 power minus 4 Simon meter square per mole. This is a question. Resistance of a conductivity cell filled with 0.1 mole per liter KCl solution is 100 ohms. They gave the resistance as 100 ohms and the concentration as 0.1 mole. If the resistance of the same cell when filled with, it's a conductivity cell, and if the resistance of the same cell when filled with a different concentration of 0.02 mole per liter KCl solution, it increased to 520 ohm. Calculate the conductivity and molar conductivity of 0.02 molar per liter KCl solution. The conductivity of 0.1 molar KCl solution is 1.28 Simon per meter. The use of this equation G star by R, which will give us the conductivity. The conductivity is found to be 0.248 Simon per meter, and concentration, which is equal to 20 mole per meter cube, because they're converting mole per liter into mole per meter cube, which we need to multiply as 1000 liters equals 1 meter cube. We'll multiply it by 1000 and we'll get the answer as 20 mole per meter cube. and lambda m equals conductivity by concentration. If we substitute, we will get that we got the value of conductivity here, which we found by using the G star by R value, which is this one. We substitute in this equation, we will get molar conductivity, which is found to be 124 into 10 power minus 4. And otherwise we can take conductivity equals 1.29 per centimeter, which is the G star value, by the resistance for this, the second one, which is actually they did the same thing again in centimeter. Here we took it as 129 per meter, but here they took it as 1.29 per centimeter. They got the value as 0.248 into 10 power minus 2 Simon per centimeter. And lambda value, taking it as molarity value, molar conductivity value, they are taking as conductivity times 1000 centimeter cube per liter and per molarity. Molar conductivity found to be 124 Simon centimeter square per mole. Otherwise they can basically, since molar conductivity is nothing but conductivity by concentration, they just substituted the values and but in conversions, and the final answer we got is 124 Simon centimeter square per mole. The electrical resistance of a column, a conductivity cell of 0.05 mole per liter, NaOH solution of diameter 1 centimeter. If they give this one the length and the diameter, we can find the G star value by L by A, and they give the resistance as 5550 ohms. Calculate its resistivity, rho, conductivity and molar conductivity via the provided values. We know that resistivity we can find by R A by L. This is rho. And as for conductivity is just inverse of rho. So after finding out rho, you can just inverse this and we will get kappa value. And as for molar conductivity, as they gave the concentration of the NaOH solution, divide by concentration, we will get the molar conductivity value. And this is basically, after doing this, they applied this formula and then this formula along with this formula to get a final answers of molar conductivity being 229.6 into 10 power minus 4 or 2.3 into 10 power minus 1 or 0.23 Simon meter square per mole, and a conductivity of 1.148 Simon per meter and a resistivity of 87.135 or 0.87 ohm meter of resistivity. And the next topic we will be going to is variation of conductivity and molar conductivity with respect to concentration. As we already know that molar conductivity is kappa by concentration. As such, molar conductivity will always depend on concentration, and conductivity will also depend on concentration. As more the number of concentration, more the number of the electrolytes, more the conductivity. As such, even conductivity as well as molar conductivity will depend on concentration of the solution. Both conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity always decreases with decrease in concentration, both for weak and strong electrolytes. Basically, they are saying that kappa is directly proportional to concentration for both strong as well as weak electrolytes. In strong electrolytes, we see that the strong electrolytes meaning 100% dissociation. And alpha value being 1. Weak this example being NaCl, KCl, etc. And weak electrolytes being acetic acid, which show less than 100% of dissociation, constant degree of dissociation, and a value of less than 1 being equal to the degree of dissociation and showing less than 100% dissociation. Definition for weak and strong electrolytes. This can be the conductivity always decreases with decreasing concentration, both for weak and strong electrolytes. This can be explained by the fact that the number of ions per volume carry the current in a solution decrease on dilution. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of a solution kept between two platinum electrodes with unit area of cross section at a distance of unit length. Let's read it again. Both conductivity and molar conductivity change with the concentration of the electrolyte. Molar conductivity depends like this. Conductivity is directly proportional to concentration, both for strong and weak electrolytes. Conductivity always decreases with decrease in concentration, both for weak and strong electrolytes. This can be explained by the fact that number of ions per unit volume that carry the current in a solution decreases on dilution. If in a solution there is a solution, the solution is 0.1 molar, let's assume. In this kind of solution with a concentration of 0.1 molar, it is nothing but we can find 0.1 mole of the solute per 1000 liters of the solution. 1000 milliliters of the solution or 1 liter of the solution. In 1 liter of the solution, you can find 0.1 mole of the compound. As we keep on diluting these are the ions, ionic content. Let's assume the electrolyte is 0.1 molar, so it contains 0.1 mole of electrolyte per liter of solution. As we keep on diluting, per unit volume, for example, this is more reduced. In this, if we take the concentration of electrolytes will be even more reduced. If this is the concentration in 0.1 molar and we diluted it further, then if we take the electrolytes in this kind of area will be reduced. As electrolytes are the main reason for conductivity or conductance, as the number of electrolytes per unit volume reduces, the conductivity also reduces. As such, higher the concentration, higher the kappa value or conductivity value, lower the concentration, lower the conductivity value. That is what they are saying here. This can be explained. Conductivity always decreases with decrease in concentration, both for weak and strong electrolytes. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution decrease on dilution. The number of ions per unit volume that carry the current in a solution decrease on dilution. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution kept between, basically this much what I said here. And the second sentence, the conductivity of a solution kappa value at any given concentration, the concentration may be anything, is the conductance of 1 unit volume of solution kept between two platinum electrodes with unit area of cross section at a distance of unit length. So they're saying that the conductivity of solution at any given concentration is the conductance G equals conductivity A by L. G equals Ka by L. Platinum electrodes with unit area of cross section, they're defining that A is the area of the platinum electrodes of cross section area A, and length distance between the platinum electrodes is L, where kappa is the conductivity and G is the conductance. This is clear from the equation, same equation. G equals Ka by L and G equals kappa, or conductance equals conductivity only when and when area is 1 meter square or unit and L is 1 meter. And this happens, we can see that R in unity, G equals K. Molar conductivity of a solution at a given concentration is the conductance of the volume of V of solution containing 1 mole of electrolyte kept between the two electrodes with area of cross section and distance of unit length. Therefore, molarity lambda m equals Ka by L equals K. Basically, let's read it again. Molar conductivity of a solution at a given concentration. Molar conductivity, we know that molar conductivity lambda m equals conductivity per concentration. This is the definition. Molar conductivity of a solution at a given concentration is the conductance of the volume V of solution. Molar conductivity of a solution at a given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte kept between two electrodes with area of cross section A and distance of unit length. Therefore, another definition they are giving for molar conductivity is that lambda m is equal to conductance of the solution G, and we know that conductance of solution is conductivity A by L, and when A and L are equal to 1 meter square by 1, then equals conductivity. Exactly what they wrote here. since L equals 1 and A equals V, where V is the volume containing 1 mole of the electrolyte. Lambda m can be written as K into volume. Basing on this equation, molar conductivity increases with decrease in concentration. Molar conductivity increases with decreasing concentration. This is because the total volume V of solution containing 1 mole of electrolyte also increases. Basically, yes, we saw that lambda m molar conductivity equals conductivity times volume. As concentration of the solution decreases, volume of the solution will increase, right? So we can say volume is inversely proportional to concentration of the solution. As concentration decreases, volume will increase. Basically, we are diluting the solution. The solute present in the solution will be 1 mole itself, but we are diluting the solution, so we are increasing the volume. Do not get confused. Here, molar conductivity increases with the increase in volume. As volume increases, here we see that molar conductivity is directly proportional to volume. But another case we saw that conductivity is inversely proportional to volume and directly proportional to concentration. Before we saw that conductivity is proportional to concentration, but molar conductivity is proportional to volume. As the concentration decreases, as the volume increases, molar conductivity also increases. I'll be erasing this. That is what they will be giving here. Molar conductivity increases with the decrease in concentration. This is because the total volume V of a solution containing 1 mole of electrolyte also increases. As concentration decreases, volume increases because we are diluting the solution. It has been found that decrease in conductivity on dilution of solution is more than compensated by the increase in its volume, because we see that molar conductivity depends on conductivity as well. As conductivity depends on concentration, as concentration decreases and volume increases, molar conductivity should decrease, right? But we see that volume is increasing, so it is seen that on dilution, conductivity decrease is more than compensated by the increase in its volume. Physically, it means that at a given concentration, molar conductivity can be defined as the conductance of the electrolytic solution kept between the electrodes of a conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of electrolyte. When concentration approaches 0, the molar conductivity is known as limiting molar conductivity. Let's read again. Physically, it means that at given concentration, molar conductivity can be defined as the conductance of electrolytic solution kept between the electrodes of conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches 0, a molar conductivity is known as limiting molar conductivity. As we see that as concentration is inversely proportional to volume. As volume increases, concentration decreases, right? So if there is a solute, there is a solution. In this solution, there is a solute of 0.1 molar. That means there is 0.1 mole of solute per 1 liter. But if this became 1000 liters, the solute will be reduced. Solute will become 0.001. It will reduce 0.0001 molar if the solution increase. This is what we call dilution. And what if this becomes 1 million liters? It will be 0.00001 or something like that, right? As we continues to increase the volume of the solution, concentration will continue to approach 0. As the solution reaches infinite dilution, as the solution reaches infinite dilution, or the concentration of the solute approaches 0, this one, conditions, either the concentration of the solute approaches 0 or the solution reaches infinite dilution, the molar conductivity is known as limiting molar conductivity and is represented by lambda naught m. The variation in molar conductivity with concentration is different for strong and weak electrolytes. It is seen in this graph. Here this is a molar conductivity versus C half for root C for, this is C power 1 by 2, nothing but root C, root of concentration. For acetic acid, weak electrolyte, and potassium chloride, strong electrolyte in aqueous solutions. When the concentration is close to 0, when we see KCl, that it has a defined conductivity of close to 190 or 180, and as the concentration of the solution increases, the molar conductivity continues to decrease. This is as we know, molar conductivity is directly proportional to volume. As volume increases, molar conductivity also increases, and as the concentration of the solute keeps on increasing, the volume keeps on decreasing. When the volume is close to when the concentration is close to 0, KCl has the peak here, which is 180, and as the concentration keeps on increasing and the volume keeps on decreasing, molar conductivity, also see that it's a downward curve, but it's not very exponential or anything like that. It's just a normal insignificant decrease or less decrease. This is seen in case of strong electrolytes, 100% dissociation. strong electrolyte. But in case of weak electrolyte such as acetic acid CH3COOH, we see that when the concentration is less, is close to zero, when the volume is very high, then we cannot find it. It's a rectangular hyperbola, means just keeps on increasing. We cannot find through a graphical method or through limiting molar conductivity as such, we cannot find the value of the molar conductivity of weak electrolytes. Strong, we have a direct value close to 200 here for KCl, but for weak electrolytes it keeps on going. It's a rectangular hyperbola. As such, we cannot find the limit molar conductivity in case of weak electrolytes in this method. This method only works for strong electrolytes. Let's continue. Strong electrolytes. For strong electrolytes, this is for strong electrolyte case, molar conductivity increases slowly with dilution and can be represented by the equation molar conductivity equals, and this symbol is limiting molar conductivity when the solution reaches infinite dilution or the concentration of solute approaches zero. Lambda naught, it is represented by lambda naught minus A root C, where A is the area. No. A is a constant. A is a constant for a given solvent. The molar conductivity for strong electrolytes equals the limiting molar conductivity minus A root C. This is root C, where C is the concentration term. It can be seen that if we plot molar conductivity against root C, we obtain a straight line with intercept equal to limiting molar conductivity and slope equal to minus A. This is the slope for the minus molar conductivity. This is for strong electrolyte. And let's continue. We obtain a negative slope. The value of the constant A for a given solvent and temperature depends on the type of electrolyte, that is charges on the cation and anion produced on dissociation of the electrolyte in the solution. Thus, NaCl, CaCl2, MgSO4 are known as 1-1, 2-1, and 2-2 electrolytes respectively. This value of A which is a constant, depends on the nature of the electrolytes, which is dissociation, the charge on anions and cations after dissociation, or dissociation, which is, for example, if we take in case of NaCl, CaCl2 and MgSO4, in NaCl we see that it is 1:1, and in CaCl2 it is 2:1, and MgSO4 it is 2:2, because 2 electrons, it is 2 plus and 2 plus charge, and CaCl2 we see that calcium will gain a 2 plus charge, and Cl minus will gain a 1 plus -1 charge. Here it is Na will gain +1 charge, whereas Cl will gain Cl minus, so it is -1 charge. So it is 1 minus 1, 2 minus 1 and 2 minus 2 electrolytes respectively. All electrolytes of a particular type have the same value for A. For example, if we take for a particular type NaCl and KCl, both will be 1 minus 1 type itself, because when dissociation Na will have plus 1, K will also have plus 1 and Cl will have minus 1. The Cl from KCl will also have minus 1. Okay. The molar conductivity of KCl solution at different concentration at 298 Kelvin are given below. Yes. Show that a plot between molar conductivity and root C is a straight line. Determine the values of limiting molar conductivity and A for KCl solution. We have the equation: the molar conductivity equals limiting molar conductivity minus A root C. So we can use that equation here for finding the limiting molar conductivity. As for the graph is here, graph for KCl, and show that the plot molar conductivity and root C is a straight line. Determine the values of limiting molar conductivity and A, constant A for KCl. Taking the square root of concentration, we obtain these values. A plot of this, and it is indeed a straight line with a negative slope. Okay. Yes, they found the value of slope equals 87.46 Simon centimeter square per mole, and limiting molar conductivity to be 150.0 Simon centimeter square per mole. See here, this, as the concentration is 0, as it's approaching 0, this point is where we have the limiting molar conductivity. As this is 149.8, this point we can approximately take it as 150. As such, the limiting molar conductivity is 150 Simon centimeter square per mole, and the slope, if we find, it will be 87.46 Simon centimeter square per mole. And let us continue. The next topic will be Corlash law. Corlash examined limiting molar conductivity values for a number of strong electrolytes and observed this we are doing for we found out that we can find out KCl, we can find out limiting molar conductivity or this graph easily for strong electrolytes. But what about weak electrolytes? As this keeps on continuing, we cannot find the value in this method or using this kind of equation. So Corlash derived a method for finding the limiting molar conductivities for weak electrolytes. So let's continue reading. Examined limiting molar conductivity values for many strong electrolytes and observed certain regularities. He noted that the difference in limiting molar conductivity of the electrolytes NaX and Kx for X is nearly constant. For example, at 298 Kelvin, limiting molar conductivity of KCl minus limiting molar conductivity of NaCl equals limiting molar conductivity of KBr minus NaBr. Sodium bromide and potassium bromide. This difference will be equal. Why? Because we saw here that the A values here we saw that A depends on the charge obtained here. So here we saw NaCl and KCl. we obtain the same, and here as well. And for example here, NaX and Kx after dissociation will have the same charge, and X is nearly constant. And here he took difference between the limiting molar conductivities from KCl and NaCl and potassium bromide and sodium bromide, and along with, as he took the difference between not only potassium chloride and sodium chloride, along with potassium bromide and sodium bromide, along with potassium iodide and sodium iodide, which all came to be approximately 23.4 Simon centimeter square per mole. And similarly, it was found that the limiting molar conductivities of sodium bromide minus sodium chloride equals potassium bromide minus potassium chloride, which is approximately equal to 1.8 Simon centimeter square per mole. Yes. On basis of the above observations, he enunciated Coriolis law of independent migration of ions. The law states that limiting molar conductivity of an electrolyte can be represented as a sum of the individual contributions of anion and cation of the electrolyte. Thus, if limiting molar conductivity of Na plus or sodium ion and limiting molar conductivity of chloride ion or limiting molar conductivity of the sodium and chloride ions respectively, these are symbol denotions, then the limiting molar conductivity of sodium chloride is given by the total limiting molar conductivity of NaCl can be given by the limiting molar conductivity of Na plus limiting molar conductivity of Cl. In general, if an electrolyte on dissociation gives V plus cations and V minus anions, then its limiting molar conductivity is given by molar conductivity equals the number of V plus number of the limiting molar conductivity of the cations plus the V minus number of limiting molar conductivity of anions. Here lambda plus and lambda naught minus are limiting molar conductivities of the cation and anion respectively. For example, here they took lambda Na plus and lambda Cl minus, and here they can take other values like Mg for plus and sulfate, SO3, etc. for here. The values of lambda naught for some cations and anions at 293 Kelvin are given in the table 2.4. These are some values. So basically, what is Coriolis law meaning? That for finding the limiting molar conductivity of electrolytes, we can find that the limiting molar conductivity, we can find sum of the limiting molar conductivity of the single anions or plus cations. This is the main law of independent migration of ion. The law states that limiting molar conductivity of an electrolyte can be represented as a sum of the individual contributions or individual limiting molar conductivity of anion and cation of the electrolyte. And what observations he did, meaning he observed that for NaX and Kx, molar conductivity differences is same in this case as well. As such, he concluded that the electrolyte limited molar conductivity is equal to the sum of the individual limiting molar conductivities of the cations and the anions. And this is the general formula. And some of the individual cations and anions molar conductivities are given. Of here, the SI unit being Simon centimeter square per mole, same as the limiting molar conductivity of an electrolyte, as both are the same. And here, yes, for cations, in cation section we see that the molar conductivity of H plus is 350 being the highest and sodium plus being 50 the lowest. And in the anion section we see that OH minus having the highest molar conductivity, limiting molar conductivity, and acetic ion, the CH3CO minus ion, having the least molar conductivity, limiting molar conductivity. Weak electrolytes. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentration, and hence for such electrolytes the change in limiting molar conductivity with dilution is due to increase in the degree of dissociation and consequently the number of ions in the total volume of the solution that contains 1 mole of electrolyte. Basically, for weak electrolytes, normally alpha degree of dissociation is less than 1, but as volume increases, dilution increases, alpha and more dissociation will take place. Alpha will also increase. If more ions are there per unit volume of solution, if more ions are there, more molar conductivity. That contains 1 mole of electrolyte. Number of increase in the number of ions in the total volume of the solution that contains 1 mole of electrolytes. In such cases, limiting molar conductivity increases steeply, and we saw the graph here, the rectangular hyperbola. That is a graph for the weak electrolytes, and that is what they are mentioning, that molar conductivity increases steeply. Figure 2.6. On dilution, as volume increases, molar conductivity increases, especially near lower concentrations. Therefore, limiting molar conductivity cannot be obtained by extrapolation of lambda naught, molar conductivity to 0 concentration. At infinite dilution, that is concentration C reaches 0, electrolyte dissociates completely. So we can say that for weak electrolytes, volume is directly proportional to degree of dissociation. This is alpha, degree of dissociation. This is proportionality constant. Proportionality sign. Volume directly proportional to alpha. As volume increases, as dilution increases, the dissociation also will increase, and finally this alpha value will reach 1 as the dilution reaches infinity or concentration approaches 0. These are the two conditions where alpha for weak electrolytes will be equal to 1, and one more statement we can say that volume is directly proportional to alpha. Alpha equals 1 as concentration C tends to 0. But at such low concentration, the conductivity of solution is so low. Don't get confused that conductivity is very low, but molar conductivity is extremely high. is so low, molar conductivity is kappa conductivity by concentration. As concentration tends to 0, molar conductivity tends to infinity. But that doesn't mean conductivity will increase. Conductivity will not increase. Conductivity will still decrease, as we know that conductivity is directly proportional to concentration. Yes, let's continue. At such low concentration, the conductivity of solution is so low that it cannot be measured accurately. Therefore, limiting molar conductivity for weak electrolytes is obtained by using Corlosh's law of independent migration of ions. Independent migration of ions, this is nothing but the limiting molar conductivity of an electrolyte will be equal to the individual sum of the limiting molar conductivity of the cations and the anions. The independent law of migration of ions at any concentration C, if alpha is the degree of association, then it can be approximated to the ratio of molar conductivity lambda m at the concentration C to limiting molar conductivity lambda m. Thus we have alpha equals molar conductivity by limiting molar conductivity. Let's read again. At any concentration C, if alpha is the degree of association, then it can be approximated by the ratio of molar conductivity at concentration to C to limiting molar conductivity. Alpha equals molar conductivity by limiting molar conductivity. But we know that for a weak electrolyte like acetic acid, Ka equals C alpha square by 1 minus A. If you remember, when alpha is extremely low, extremely smaller than 1, alpha here is neglected and Ka will become equal to C alpha square. And here as well, basically this is alpha value, and here they substituted the alpha value. And we can write like this. Applications, the next is the application of Corlosh's law. Using Corlosh's law of independent migration of ions, it is possible to calculate limiting molar conductivity for any electrolyte from lambda naught of individual ions. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know the limiting molar conductivity and molar conductivity at a given concentration C. Basically, he is saying with use of this formula we can find the concentration for any kind of weak electrolyte. The limiting molar conductivity of any kind of weak electrolyte can be found out, and also along with degree of dissociation also can be found out if you know the molar conductivity as well as the limiting molar conductivity. And for strong electrolytes as well, if you want to find out the molar conductivity of a strong electrolyte, you can use the individual cations and anions contributions to find out the electrolyte, the molar conductivity of the electrolyte. This is the sum. I will not be showing the sum. Actually, yes, let's go. Yes, now the in-text question, why does the conductivity of a solution decrease with solution? Here, as I showed, if there is a solution of 1 molar containing an electrolyte, this is a unit of solution. There are many electrolytes here, but as we increase the dilution, this is a tank and there is so much dilution, and if we take only this many molecules will be there. As less electrolytes, then less the conductivity. As such, conductivity is directly proportional to concentration. As we increase the dilution, the concentration of the number of electrolytes per unit volume will decrease and the conductivity will also decrease. Suggest a way to determine the limiting molar conductivity value of water. As water is not a strong electrolyte and a weak electrolyte, we can use the Coriolis law along with this formula, dissociation constant equal lambda m by lambda m naught, and we can find, and we can, if we shift this, we can get limiting molar conductivity equals lambda m molar conductivity by alpha. This is one of the methods, or using this equation, if we know the equilibrium constant, then we can find the limiting molar conductivity value of water. They did not ask us to find, they just said a way to determine. So it is one of the ways. The molar conductivity of 0.025 mole per liter, that is molar, 0.025 molar methanoic acid is 46.1 Simon centimeter square per mole. Calculate its degree of dissociation and dissociation constant given lambda naught H plus equals 349.6 Simon centimeter square and lambda naught for HCOO minus equals 54.6 Simon centimeter square per mole. We know we got the individual ions limiting molar conductivity. So with this, if we add these both, we will get the limiting molar conductivity of the methanoic acid, and by that we can get the degree of dissociation via this formula. If we add, the limiting molar conductivity is nothing but the addition of the individual ones. The limiting molar conductivity of cation, which they gave for H plus as 349.6, plus the limiting molar conductivity of minus, which is the HCO minus, which they gave us as 54.6 Simon centimeter square. This both, if you add, you will get the limiting molar conductivity of the methanoic acid and this methanoic acid one, and they already gave the molar conductivity of methanoic acid, which is lambda m they already gave. So if you substitute in this equation where molar conductivity by limiting molar conductivity, you will get the degree of dissociation, which is one of the thing they asked, and dissociation constant, which is nothing but K alpha, which you can find out by this equation. Just substitute the values and you'll get. And the next concept, electrolytic cells and electrolysis. Which we will be doing tomorrow. Have a good night. I will be ending the